All right. Hi, everyone. So today we're going to go through an example of a non-regular language, a language that cannot be detected by a finite automata. And we'll start to see why that is not the case, even though it seems like this very clearly should be a problem that a computer can solve. But the fact that a finite automata cannot means that clearly there is something more to be desired or expressed in terms of our model of computation than what finite automata by themselves can provide. And the language that I'm going to ask us to consider is the language where we have an equal number of zeros followed by an equal number of ones. So some number of zeros followed by an equal number of ones. So the elements of this language would be the empty string, because k could be 0. We could also have 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. Okay, so this is our set of strings that should be recognizable. It is an infinite set, like many of the other regular even regular languages that we have examined in the past. But this one is not regular. And to see why, we have to remember that the most important property of a finite automata is that it is finite. And the number of states that it has must be predetermined before we see the input string that we are trying to recognize. So, as a proof by contradiction, to show that this language is not regular, let's assume that there is some magical finite automata M that recognizes this language. And we know that M must have some finite number of states. So we will say that M has n states. Now the question is, what happens if k is larger or equal to n? So let's say, suppose that k is greater than or equal to n. So we'll consider just the case for now of the string n copies of 0 followed by n copies of 1. Well, the issue here is, in order for this to work, essentially we've got a finite automata that must have a path from its start state to some accept state with a path length. So we will take in some number of inputs. Every input we will move to a new state, ... And then a couple more. This is a transition point which will become relevant in a moment. So we've got some path here that says, well, this is number 0, and this is number 2n, after we've accepted 2n inputs, n zeros followed by n ones. Well, that means that there must be some dividing line here where this is after accepting the nth input, and this is after accepting the nth plus 1 input. So somewhere in the middle here, we had to accept our first 1, and all of the rest of these must have accepted zeros. Or must have read in zeros, not accepted them, because we don't accept until we are done reading the entire string. Well, just looking at this section here, how many states did we visit? Well, we started at state 0, or we started at some state, I'll call it Q0, and then we went to some other state, let's call it Q1, and we kept going until we got to some state here. How many total states is that? Well, we went from 0 up to n. In all of this together, there are n plus 1 states that we visited. But we just said earlier that our magical finite automata that recognize this language only has n states. That means we must have repeated one. Somewhere in here, there must have been 2 instances of state K for some state. Don't know which one, but we know that we had n plus 1 things that we visited one by one, and there are only n states in together, which means one of them must have been repeated. But what does that mean? Well, it means that however far apart those 2 repeated states were, there must have been a loop that will accept some number of zeros. I'll just call it the 0 loop. So somewhere in here, we must have had some state K that by taking a bunch of zeros, we looped back around to state K. Which means that we could have done a few other things as well. We could have given another string. Let's say that there are X number of arrows in here that will cause us to repeat this. Well, if there are X arrows, then that means that I could have had n minus x 1n, and that would have worked fine, because that would have just mean that we didn't follow this loop, and we just went straight from state K to whatever the next state was. But that's not a part of our language. Which means that this finite automata does not accept exactly this language. Because in order to accept exactly this language, it would have to reject this language. But it doesn't reject this language, it doesn't reject this string. It accepts this string. Which means that we've reached a contradiction. We assumed that there was a finite automata that recognized exactly this language, and we showed that based on that assumption, actually that's not possible. This finite automata can't accept just this language. It has to accept some other strings in addition that are not a part of this language. So assuming that there is a finite automata that will recognize this language led to a contradiction, which means that it is impossible for there to be a finite automata that recognizes this language. And again, the reasoning behind it was effectively because we needed to know ahead of time how many states this finite automata would have before we saw the input. Now, if we had put any kind of limit on this, let's say that k must be less than or equal to 100 or 1,000 or 1,000,000. You put any number as an upper limit on k, and you can do that perfectly fine. You can say, at most, this many repetitions of 0, followed by an equal number of repetitions of 1. That would be a regular language. But the fact that we have no limit means that there is no finite number of states that would be sufficient in order to recognize this infinite space of strings. Now, the infiniteness isn't necessarily a problem. Any regular language using the star operator may involve infinitely long strings. But those are perfectly fine in our system because those star operators just lead to loops. We accept it once and then maybe accept it some more. But the problem with this system is that we're not just replicating one thing, we are having an arbitrary amount that we need to remember from all of the zeros before we can start accurately evaluating the ones. And that's not going to work with a finite number of states. So I hope that gives you a little bit of an idea, and that this basic proof idea leads into the more general pumping lemma that the textbook describes, that we can use to show any uh, program, any language that isn't regular is in fact not regular. It is the most powerful tool that we have to show that a language is not regular, but hopefully this simpler example illustrates some of the basic idea of where that pumping lemma comes from in the general case by showing how the proof that this particular language is not regular, involving things like cycles in the language and what happens when you remove or put in those cycles. So I hope that helps give some context, and I will talk with you all again soon.